Last time I was talking about bases. So there are some axioms for bases of a matroid. So the first one is that it's non-empty. And the second axiom is the exchange axiom, which is that if I and j are two bases and I is any element in one but not the other, then you can find an element in j which is not an I, such that you remove I or replace it with j, and you get another basis. That's the exchange axiom. And how do you go, if you know the basis, how do you find the independent sets of your matroid? Subsets of bases. All right, cool, thanks. So just indeed, you take all subsets of all bases. If you know the independent sets, how do you get the basis? Okay, you take maximal by inclusion, independent sets. And what about if I have a graph? If G is a graph, then the bases of the corresponding graphical matroid are what? Yeah. Okay, yeah, right. All graphs are going to be connected. So yeah, then the spanning trees. Thank you very much. And yeah, let me add one more system of objects to define matroids. So far we had independent sets and bases. Let's do one more. And the other one is going to be circuits. A circuit of a matroid. So bases are maximal independent sets. Circuits are minimal dependent sets. Circuit of M is a minimal by inclusion dependent set of M. And what do I mean by dependent? I mean not independent. Independent, M is given by a collection of independent sets. All the other ones are called dependent. Okay, so and I'm going to denote E of M, the set of circuits of M. And in particular, if you take a connected graph, G is a connected graph, what's going to be the set of circuits of the corresponding graphical matroid? Which cycles? Cycles containing all the vertices. That's actually not quite true. I mean, it's close, but like, I mean, if I give you a graph like this, surely, like if I take all the edges, I'm going to get a dependent set. Because independent sets are forests. The whole graph is not a forest, but there isn't a cycle that contains all the edges unless you're allowed to kind of go back and forth, or yeah, it's every vertex and has a cycle. Yeah, so a dependent set indeed has to have a cycle, but a circuit is a minimal dependent set. Exactly one cycle. Yeah. So first of all, what do you mean by a cycle? Is is this a cycle, or what's a definition of a cycle? Okay, all right. Yeah. Anyways, the answer is, I mean, yeah, the answer is the set of simple cycles in G. Yes. Plain old simple cycle. Yeah, it just means just a path which doesn't intersect itself except that the start point is equal to the end point. And that, because so these three edges, the corresponding three vectors, sum up to 0. So that's a linear dependence in your vector configuration. So the circuits of a matroid represent minimal linear dependencies of your vector configuration, or minimal affine dependencies of your point configuration. And maybe we should try another. Yeah, let's do 1, 2, 3, 4 equals to 5. What is the set of circuits? Or 5. Okay. 1, 2, 3. Okay. Anything else? Okay, so is 1, 2 a circuit? Is it 1, 2 dependent or independent? Yeah, they are affinely independent. Right? They belong to the same. This line is represented, and these three are dependent together. Yeah, I could remove that line. Yeah. I mean, I can draw as many lines as I want. But I mean, you're right. Yeah, I should have drawn. It would be more clear to draw it like this. That's it. Okay, that is correct. So, how do you characterize cycles of Matroid by axiom? Let's do this here. Let me just do it. Proposition: if you have a collection of sets, collection of subsets of the ground set E, then the claim is that this is a set of circuits of a matroid if and only if I'm going to have three axioms. The first one is trivial. The empty set is not a circuit. The second axiom is, because the empty set is independent by definition. The other claim is that if you have a circuit, basically a subset of a circuit is not a circuit. You have J subset, a proper subset of C, and it's not a circuit. And finally, the exchange axiom. Anybody want to guess the exchange axiom? Let me give you the first part of the axiom. Let's say you have two circuits, C1 and C2. The circuits, and then let's say they have an element in common. Okay. Indeed, if I draw a graph, C1, C2, And then if this is x, then if you take the union of C1 and C2 and you remove x, then the result contains a circuit. C1 union, yeah, that's actually correct. There exists another circuit, C3, such that it's contained inside the union of C1 and C2 without x. Precisely correct. And so why contained? Why? I mean, in this case, it's just the C3 guy would just be here. Right? Is it always just equal to the union without the x? So, okay. Okay. Yeah, again, I can understand every second word of what you're saying. And, okay, yeah, right. So I have an edge and an edge. Goes this, 2, 1. And then maybe this edge here is x. Then the union without the x, there's actually two cycles. C3 here, or maybe C3 prime. There are several candidates for C3. And you could imagine a more complicated configuration where there's like many different, maybe some common vertices somewhere else, or yeah, the graph does not have to be planar, so you could imagine all kinds of cross intersection between C1 and C2. Yeah, but the axiom is that the union without the x contains a circuit, and that's actually, yeah, maybe I should write it down. I want to keep my axioms, but I don't want to erase a whole lot of things. C1 means the empty set is not a circuit. C2 means a subset of a circuit is not a circuit, a proper subset circuit. And the exchange axiom is that if you have C1, C2, two circuits, they have an intersection, then I can find another circuit which is contained C1 and C2 without. All right, how do I go? So I know how to go between independent sets and bases. How do I go between circuits and independent sets? Let's say I have independent sets, and then I want to go back and forth between with the circuits of the matroid. How do I go in this direction? If I know the independent sets, what are the circuits? Okay, like minimal, dependent. If you want to go the other way, how do you recover the independent sets? Remove one element and take all subsets. Yeah, that actually works. Situation where all sets are independent Yeah, I see. So you're saying if you just take n vectors which form a basis, then okay, yeah, that doesn't quite work. If my vectors form a basis, the set of circuits could be empty, unlike yeah. Yeah. So what's the yeah? How do I make it precise? Uh, okay. All right. All right. Yeah. Let me write what I think is equivalent but slightly different. So an independent set is a set which does not contain a circuit. And independent means independent. It does not have a linearly dependent set inside of it. Does not contain a circuit. All right. How about going between bases and yeah? Okay. Right. So indeed, yeah, that was actually not good. So if I have a graph like this, then I have an independent set which looks like this. Uh, yeah, so, right, okay, so, yeah, basically I can take, well, I mean, this works. All right. If I want to go, if I know all the bases, how do I find all the circuits? Yeah. Oh, interesting, right. So what happens if I take a basis and I add an element which is not in the basis? Minimal circuits, minimal sets not contained in the base. Yeah, that's actually, yeah, so I get, this arrow actually, these arrows actually basically go through the correspondence between basis and independent sets. So yeah, it's a circuit is a minimal element which is not contained in the basis. And if I want to find the basis from the circuits, what do I say? Maximal set doesn't contain a circuit. Okay. Maximal not containing a circuit. Okay. Yeah, so it's good to practice this uh, for a while to just kind of quickly be able to convert different axioms. Yeah, by the way, so this gives you another, yeah, the proposition is that this gives you matroids as well. So now we have three different systems of axioms which all give you the same object. And I haven't proven any of that, but that's, you can, there's an exercise. All right, now, because the reason I'm not proving any of that is I want to tell you some interesting stuff. So the interesting statement that I want to make right now is the duality. Duality for matroids. As you remember, in the first lecture or whatever, yeah, we were talking about what's the dual of an arbitrary graph, which may not be planar. So, okay, here's the statement. Let M be a matroid. And then, how do I define the dual matroid? This is also possible to guess. Yeah, I'm gonna define the basis of the dual matroid. Say it again. Perfect. Yeah, that's exactly correct. Yeah, take the complement of every basis of your matroid. So then the claim, then the star is the set of bases of a matroid, which is denoted M star. So that's called the dual matroid to my original matroid. Just take complement of every basis. And how did you come up with it? Or what was the reason you? Okay, just intuition. All right. Yeah. So you're saying if the matroid comes from some vector configuration, or? Yeah. Right. Yeah. So that actually it's a good question. Like, what happens if I give you a bunch of vectors? Some of them, maybe these two are parallel. The sum is 0, 1. Something like this. What's the dual matroid of such a picture? Like here, 1, 2 is a basis, so 3, 4, 5, 6 should be a basis of the dual matroid. Yeah, I'm gonna answer this question maybe in the next lecture, but for yeah, this is a good question. Actually, it's not non-trivial to see what this does. But maybe let me try another example, which most of the time. So the claim is that it's a set of bases of some matroid. So there exists a matroid where 3, 4, 5, 6 is a basis. Yeah, yeah. So in particular, what if you remember, did you define the rank of a matroid? Okay. So what is the rank? The rank of the dual matroid. Size of E, thanks, minus the rank of the original matroid. So and the ground set is the same. I preserve the ground set. All right. So what happens when if I take a graph? Let me draw a random graph, and I wanna take a planar graph for some maybe something like that. And I want to label the edges. So vertices are here. A, B, C, D, E, F. This is my graph G. So what is the set of bases of the corresponding matroid? So let's say my matroid is the graphical matroid. Can you tell me the set of bases? B, C, D. B, C, B, C, F. B, D, E, B, D, F. Okay. Now, what about the dual matroid? Say it again. AEF, ADF, ADE, BC, ACF, ACE. All right. So what is the meaning of this operation? Let's actually make some. Yeah, go ahead. For every planar graph, there's a dual graph. Okay, interesting. Okay, let me try to draw the dual graph. Okay, is that right? Hmm? Okay, and then this is A, B, C, D, E. Let's see. A, E, F. A, E, F. Oh, what was the dual of a planar graph? Uh, so yeah, every face I put a new vertex on every face. So there's 4 faces. I put 4 vertices, and then every edge separates one face from the other. Could be the same faces, could be different, and then I connect. So for every edge, there's a dual edge which connects the two. Yeah, in particular here, so you see that A is a loop in the original graph, which means that it never appears in any of the spanning trees, and A appears in all spanning trees here, and that's because if you remove A, the graph becomes disconnected. That's called a call loop. I'm going to talk about these later. And similarly, B was a call loop in the original graph, and B is a loop in the dual graph. And yeah, you can check that all these 5 bases are precisely the 5 spanning trees of the dual graph. And yeah, so that's an example. I'm also gonna, yeah, I mean, that's a general theorem. Matroid duality for planar graphs, it generalizes planar graph duality, planar duals graphs. And there's actually some subtleties. So I should probably, yeah, let me try to mention them right now. So I'm gonna try to prove this theorem. But before I do that, let me talk about bases can be right. So what if my graph? Oh wait. Oh, first of all, right. So the set of bases should be non-empty, which so if you have a graph with several loops, A, B, then the set of bases is what is the set of bases? The set of bases cannot be empty by definition, but it contains the empty. It consists of the empty set. In particular, the dual basis is AB, and the corresponding graph looks like this. Yeah, for Matroid, it's very important for the definitions to work for all degenerate cases, because we're gonna here. Right, the dual. Okay, so well, yeah. So B is a loop here, for example. Right. Okay, so yeah, so the thing I want to mention before I talk about the proof is what do you mean loops in the ambient space? Okay, yeah, so you should think of this as drawn on a sphere, maybe, so that the whole picture is symmetric. Yeah, there is one outer face which is no different from any other. All right, so indeed there is a proposition which is that if G is a planar graph, and then you take G star to be the planar dual, and then the claim is that the dual matroid of G is the same as the matroid of G star. And yes, so if I write something like this on the blackboard, you should start complaining. There is a problem with this statement which you should start asking questions about. What if G is not? Yeah, let's assume connected. G star is, well, could it be not connected? Yeah, I think it's going to be connected, right? Yeah, I have to think about it. Yeah, let's assume it's going to be connected. Hmm? But no, there should be a serious problem with this. Yeah. So could you explain what you mean by not unique? Right, so a matroid is actually fully determined by its set of bases. Yeah. I should mention that the ground set the dual same as very nice. Okay, yeah, that's exactly the problem. So the problem here is that not only do you have to specify a planar graph, but actually you have to specify how it's drawn in the plane. If it's drawn in a different way, it could be that the planar dual is just a different graph. And an example here is if G looks like this, or G looks like this, it's the same graph, right? But the planar dual planar duals are not the same. And the easy way to see that they're not the same, if you look at the degrees of all like this vertex has degree 6. There are 6 edges. And the degrees are 6, 4, 3, and 3. Here they are 5, 5, 3, and 3. So the dual graphs are not isomorphic. Okay, so what's the conclusion? Is the statement clearly wrong, or is there a way to make it true? Every single planar dual is what? Okay, right. So there could be Okay, yeah, so the actual, so this statement is still true as stated, where you choose some planar embedding and the resulting dual matroid, the matroid of the dual graph does not depend on your embedding for some reason. This is, yeah, so. Yeah, so yes, the spanning trees of G, their complements are always going to be the spanning trees of G star, no matter which embedding you choose. The explanation. All right. Yeah, so in the remaining 13 minutes, I wanna try to prove this duality theorem and just see what happens, what exactly goes into the proof of this statement. Because I need to show that the new collection of these complements gives me a matroid. And so the main purpose of this proof is I wanted to choose a statement to just play with the axioms so that I could, yeah, if you want to work with matroids, you have to actually apply these axioms a lot. And I want to demonstrate that. So I want to give you the proof of this statement here. And okay, so what do I need to show? I need to show the goal is to show that B star satisfies the axioms. Right? B1 and B2. Clearly, it satisfies B1. Okay? Clearly, if you take complements, yeah, B star has as many elements as B. B1, clear. What is B2? B2 tells me that, okay, so for each I and j in B star, and for each I in I minus j, there exists j in j minus I, such that I take away I union j is in B star. Okay, and now I want to convert this into a statement about B. So I want to take, Nice. Yeah, okay, right. So if I replace I with I complement and j with j complement, then these two are going to swap. I is going to belong to, yeah, let me write down the dual statement. B2 star. If you have I and j in B, where here I've replaced I and j with the complements, and if j is in j minus I, then there exists I in I minus j, such that I minus I union j is in B. So yeah, I did some replacement, which the goal was to make two statements look very similar. Here I and j are swapped, and here I and j are swapped, but this is the same. So previously I had for each I there exists a j. Here I have for each j there exists an I. You can replace I with j in capital I. Now this is not the same axiom as B2. It's a different statement, and you have to prove that the original set of bases which satisfies usual B2 also satisfies this dual B2. So how do I prove this? And if you try to prove it directly from bases, it's actually pretty non-trivial. So what we're going to do is we're going to take advantage of all the different axiom systems. Namely, I'm going to go from bases to circuits, prove a statement about circuits, and then go back to bases. Here. And what is the lemma about circuits that I want is, well, let's say lemma about circuits. Let's say you have an independent set and you have an element E, which is not, so E is not an I, then suppose that if I add E to I get a dependent set. Then, so the picture is that I is an independent set, which looks kind of like a forest. Something like this. This is I. And then if I add E to my set, it becomes dependent. And the claim is that, so this is related to the question we had previously. So then the conclusion is that then there is a unique circuit C such that C is a subset of I union E, and moreover, E belongs to C. Okay, so and that's a very useful lemma. Whenever you have an independent set and you add a new element and becomes dependent, then there is a circuit. It's a unique circuit you could use. Okay, how do I prove this lemma? First of all, why does there exist a circuit? Right, okay, because this set is dependent. Circuits are minimal by inclusion dependent sets, so this union contains at least one circuit. I union E is dependent, therefore contains a circuit. Okay. Why do I know that E belongs to this circuit? Right. Otherwise, I would be dependent itself, and I know I is independent. So E belongs to C, clear. And I only need to show that the circuit is unique. How do I show that my circuit is unique? Very nice. Okay, right. So if I have a different circuit, if C prime I is another circuit which contains E, then I can use the exchange axiom, which tells me that there exists a C double prime, another circuit which satisfies C double prime is contained in C1 union C2 without E. And why is that a problem? Right, because this thing is contained inside I, which is independent. Okay, very nice. All right, so yeah, I have this lemma on circuits, and now I'm gonna, actually let me denote, so since I have this operation which, if you give me an independent set and an element which makes it dependent, then I get a unique circuit. So let me denote C of E comma I by C. So if you give me an element E and a set I, then I get a circuit from this lemma, which is denoted by C of E comma I. Now, now I want to prove this B2 star. I want to prove that my bases satisfy B2 star. So let's see. I is a basis. I is independent. And I also have a set J, which does not belong to I. If I add j to I, what do I get? I get a dependent set. Because I was a basis. You can't add anything to a basis and still be independent. Okay, and therefore I have these two assumptions. So let me denote by C the corresponding circuit. Then I'm gonna, so the picture should look like this. I have some, this is I, right? And then I have some other set J, which there's another set J, an element J here, which makes a cycle. So then what I want to claim is that I want to find an element I. I want to find little I in capital I, which I can remove to get a basis. Which my question is, which elements I, little I, can I remove from capital I to add J and get a basis? Right, yeah, these could be only the ones on that circuit, and precisely those. Claim is that for any I, little I in capital I, let's remove an I and add in J is a basis if and only if I is inside that circuit. Well, actually, it's even true for J. Yeah, J is not in capital I, so yeah, I think this is true. Right, yeah, so to prove B2 star, I need to choose I, which is both in capital I and not in capital J. But so far, my claim is like, which possible basis can I get out of capital I by removing something and adding J? And the answer is, I need to look at that circuit. And now I need, now the game is to find an element inside that circuit which is not contained in J. Capital J could be some other thing, maybe contains other edge here. But what I should prove is that it can't contain all of these edges of C. J cannot contain C. And why is that? Because J is dependent. Because J is independent. So yeah, the conclusion is that we know that capital J contains little j, so there must be an element, must be a little I, which does not belong to capital J. I in C minus J such that I belongs to I minus J. That's the end of the proof. And yeah, so this should give you a general idea of how these Matroid proofs work. You just kind of juggle different sets and elements and axioms, and that's basically it. Yeah, I'm out of time, so thanks a lot. See you on Monday. Have a good weekend, everyone.